Hello friends, welcome back to my YouTube channel. In this lecture I am going to discuss about entropy balance principle, which is quite similar to energy balance principle, which we have already discussed while discussing about the first law of thermodynamics. And this entropy balance principle will be of immense use while calculating entropy change and entropy generation, and these calculations are going to be used while solving numericals based on entropy, and these questions on entropy form an important area as far as the gate exam is concerned. Before starting, I must say one thing to all of you: please do subscribe to this channel, of course like it and share it to your friends. Let's get started. So, what is actually entropy balance? You know, we know that the property of entropy, the property of entropy is a measure of molecular disorder or randomness. The more the molecular disorder in a system, the more the entropy is. So, you see, entropy cannot be destroyed, entropy can only be created. But on the other hand, energy, energy conservation of energy principle states that energy can neither be created, energy can neither be created nor can be destroyed. But if you compare this with the statement relating to entropy, you see entropy can never be destroyed but can be created. And for any system undergoing an irreversible process, some amount of entropy is created or generated. But if the process is internally reversible or totally reversible process, then there is no question of any entropy being created or generated. But during some process, there is possibility that some entropy may be created, but energy is never created during any process. That is the energy conservation principle. So this is the difference between energy and entropy of a system. So if we can write the entropy balance principle applicable for any system, this entropy balance principle applicable for any system undergoing any process can be written like this: total entropy entering total entropy entering. Entropy is an extensive property of the system. This is the total entropy, which is often designated by capital S, minus total entropy leaving the system, plus total entropy generated. Total entropy generated is equal to change in entropy. Change in entropy. In fact, it is total entropy of a system. So it can be written like this. This is an equation. Capital S in minus capital S out plus entropy generated is equal to delta S of system. This is the entropy balance equation. This may be considered as equation number 1. This is the total entropy that is entering into a system or control volume. This is the most generalized equation of entropy balance, which can be used for any kind of system undergoing any process, and this is very helpful for calculation of entropy change and entropy generation. This relation is known as entropy balance relation, and this can be stated in this way: the entropy change of a system during a process is equal to net entropy transfer through the system boundary plus entropy generated during the process, or within the system, entropy generated within the system. And if it is a reversible process, then this term will be 0. You see, these two are boundary phenomena. This is the total entropy entering into the system through boundary, and this is the total entropy that is leaving the system through boundary. So difference is the net entropy transferred into the system. This is the entropy that is transferred into the system during the process with the addition of heat or any other mechanism that we are going to discuss, that is with the mass also entropy can enter, because it is an extensive property. Whenever any mass enters into system or any mass exits the system, as it happens in case of a control volume or open system, along with mass, entropy is also transferred. But this is the total entropy that enter into control volume or open system or any kind of system, and this is the entropy that leaves the system. So this difference is the net entropy transfer. This is the net entropy that is transferred into the system plus whatever entropy is generated within the system. This, if we add these two terms, then we will find the change in total entropy of system or increase in total entropy of system. If this is plus, then this is increase, and if this is minus, this comes out minus, then there is a decrease in total entropy. So mathematically this can be stated in form of equation. This is the entropy that is transferred with heat or with mass minus S out, and this is the entropy that is generated, and this is the total entropy increase of the system. Had it been a energy balance, then there would be no energy generation term. For energy, the equation would have been E in minus E out is equal to delta E of system. There is no energy generated in any kind of system. So entropy can be generated, but it cannot be destroyed. But energy can neither be created nor can it be destroyed. So how this entropy transfer take place? Mechanism of entropy transfer. Mechanism of entropy transfer. That is, this is mechanism of entropy transfer. So how does this entropy transfer between system and surrounding take place? You see, this is suppose a system. This is a piston cylinder arrangement. This is the boundary, this is the system. So you see, along with heat as well as mass, entropy is transferred into the system or out of the system. So entropy जो है वो heat के साथ आ सकता है या जा सकता है, and apart from that, this transfer of entropy can also take place with mass, because if some mass enters into control volume or open system, then with that some entropy may enter. So दोनों के लिए two mechanisms are, two modes of entropy transfer is there. One is heat. First one is heat. You know, heat is a disorganized form of energy. So that's why with this some disorganization or some disorder enters into system or control volume. But there is no entropy transfer, no entropy transfer with work. So this is one of the difference. This is the one of the difference between heat and work interaction between system and surrounding. First law says that both these forms of energy interactions are same, but second law distinguishes between heat and work. Both heat and work transfer are energy interactions, but with heat entropy transfer takes place, but with work no entropy transfer takes place. That is the difference. So second law discriminates between heat and work, but first law does not discriminate between those two modes of energy interactions. So apart from heat also mass के साथ भी entropy transfer हो सकता है, mass के साथ भी हो सकता है. So these two are primary modes of entropy transfer into a system or out of system. So जब heat के साथ entropy आता है, suppose this is the temperature of boundary TB is suppose 400 Kelvin, and heat that is transferred from surrounding to this system is suppose 500 kilojoule. Then if this boundary temperature is constant, this temperature of the boundary is constant during the whole process, then what is the amount of entropy transferred into the system? The entropy transfer into the system will be Q divided by TB, that is 500 divided by this much of entropy is transferred. You know, the direction of entropy transfer is same as the direction of heat transfer. That means whenever heat is transferred to a system means entropy is transferred into the system, and when heat is rejected from the system means entropy is rejected from the system. So when mass transfer takes place, how entropy transfer is calculated? So for that we know that we will write the general equation that we have discussed. This is the general equation: S in minus S out plus S gen is equal to delta S of system. If you write this equation number 1 in rate form, that will be S dot in, rate form means per unit time, minus S dot out plus S dot gen is equal to ds of system divided by dt. So S dot of heat you can write that is equal to Q dot divided by T. Q dot by T, because S is only Q by T. in rate form, that will be S dot is equal to Q dot divided by T. So for unit mass, this equation can be, or this equation number 1, which is the most general equation, that is S in minus S out plus S gen is equal to delta S system. And in per unit mass form, this is small s in minus small s out plus this is small s gen is equal to delta small s system. That means this is in term of intensive entropy, specific entropy, intensive property, that is entropy per unit mass. So there is a term called total entropy generation and internal entropy generation. There is some difference between these two terms. You see, suppose if we take the system only into account, whatever entropy is generated within it due to internal irreversibility, that is called internal entropy generation. And if you take the system and its immediate surroundings as an extended system, then if any kind of entropy is generated outside the system but inside that extended system due to certain external irreversibilities, then whatever entropy is generated, if you take that into account, that will be called your total entropy generation. Suppose this is your system and I will take this immediate surrounding into, I will consider this immediate surrounding. This is immediate surrounding. I will take this immediate surrounding as a part of system. Then this system will be called extended system. And this is your surrounding. This is your surroundings. And suppose there is a heat interaction between this system and immediate surroundings, and if we are to calculate the delta S of this extended system, this system and this immediate surroundings taken together is called extended system. Extended system is nothing but this is system plus immediate surroundings. And this is also called the buffer zone. The entropy change of this buffer zone, that is the immediate surrounding, is usually small relative to entropy change of this system. This is your original system, but this is your extended system when you take this immediate surrounding inside this system, or if you consider the immediate surrounding that is next to the system as a part of an extended system, this is your extended system, and this is your buffer zone. And the entropy change of buffer zone is usually small relative to the entropy change of system and is usually disregarded. This entropy change of this immediate surrounding, that is the buffer zone, is usually neglected with respect to the entropy change of system, because this is quite small as compared to the change in entropy. So while calculating entropy transfer between this extended system and this is your surrounding, now if this is your extended system, then this is your surrounding. While calculating this entropy transfer between the extended system and surrounding, the boundary temperature of extended system is simply taken to be the environment temperature. This is the boundary temperature. Suppose this temperature is Tb. Then this temperature, the boundary temperature of extended system, is simply taken to be the environment temperature. and if this Q is transferred from this extended system to surrounding, then you will say that there is an entropy transfer of minus Q divided by TB if you consider this extended system for analysis, because the heat is transferred out of this extended system towards surrounding and temperature is to be taken TB here. This surrounding, the temperature of the immediate surrounding is to be taken into consideration. This is the boundary temperature of the extended system. And you see, if the temperature, suppose in a system there is multiple this is your system and this is surrounding, and heat transfer takes place at multiple locations, not at single locations with different temperature. Here the temperature, some heat is added or heat is rejected, whatever may be the case, but with different temperatures at different locations. Then what will happen? The entropy transfer is calculated sigma qk by tk. You have to calculate all the individual values of qk by tk and then add those values to find out the total entropy transfer, maybe into or out of the system. So for general equation we can write like this. For a closed system, suppose in case of closed system there is no mass transfer. We know that closed system is a system of fixed mass and there is no mass interaction between the system and surrounding. So now equation 1 reduces to sigma qk by tk plus S gen is equal to delta S system. Why? Because there cannot be any entropy transfer into the system or out of the system with the mass flow, because there is no mass interaction between the system and surroundings. The entropy transfer can only take place through two modes. One is through with mass and another is with heat. But energy transfer can take place in three modes. One is heat, second is work, and third one is with mass. So that is the difference between energy and entropy. So this is the relationship qk by tk plus S gen is equal to delta S system. For all adiabatic process, Q equal to 0. There is no heat interaction between the system and surroundings in case of an adiabatic process. So for adiabatic process this term will be 0. So for adiabatic closed system the equation will be adiabatic and closed. This was one for closed and adiabatic होने से Q 0 हो जाएगा. Adiabatic and closed system S gen is equal to delta S, change in entropy. So how to calculate this entropy change in case of a control volume, or you can say open system. Control volume or open system. How to calculate the, or what will be the entropy balance equation for control volume or open system. You see, this is the control volume. Control volume means both mass and energy interaction can take place. So this is your boundary, or you can say control surface also. And this is your surrounding. So this is your open system. Suppose whatever mass enters into this control volume or open system, Mi is the mass that enters in single stream and Si is the entropy of that mass, and me is the mass that leaves the control volume with the entropy, specific entropy of SE. And suppose some Q amount of heat also enters into this system, and the temperature of the boundary being T, constant at capital T, then how can we determine what is the change in entropy? Delta S Cb, by applying the equation number 1, the most generalized equation of entropy balance, will be Q by T, because Q is entering into the, here the heat is added to the system, means entropy will be added to the control volume or system, because the direction of entropy transfer and energy transfer will always be same. Whenever heat is added, then entropy is added, and whenever heat is rejected, that entropy is rejected. So that will be Q by T plus ये मास के साथ भी कुछ एंट्रोपी आ रहा है, एम आई मास एंटर कर रहा है विथ स्पेसिफिक एंट्रोपी एस आई, देन व्हाट इज द टोटल एंट्रोपी दैट एंटर्स इनटू कंट्रोल वॉल्यूम विल बी प्रोडक्ट ऑफ एम आई इनटू एस आई. This is small si is the specific entropy, kilojoule per kg Kelvin would be its unit, minus this is the entropy that enters, total entropy that enters into control volume. What are the total entropy that leaves the control volume? This is the mass that leaves the control volume, and with entropy SC. So minus MESE plus entropy that is generated, this is not in red form, entropy generation. If suppose instead of this single heat transfer from the surrounding, if heat interaction takes place at multiple locations with different temperatures, then the equation will be sigma qk by tk plus, and if instead of this single stream of fluid entering into the control volume and single stream of fluid leaving, if there is multiple streams of fluid entering and multiple streams leaving, then the equation will be like this: sigma mi si minus sigma me se plus s gen is equal to delta S Cb. Suppose for steady flow, what will be the equation? For steady flow के लिए क्या होगा? For steady flow, we will determine how to calculate the entropy generation. While analyzing steady flow, in fact, always analysis is made in terms of rate, because in steady flow there is no variation with respect to time. So now the equation number 1, if is expressed in rate form, then equation is like this: s dot in minus s dot out plus s dot gen. That means the rate of entropy that is entering into the system per unit time, rate of entropy leaving the system per unit, that is entropy leaving the system per unit time, is equal to ds by dt, ds by dt. From this, if suppose single stream of fluid entering MISI minus MESC plus S gen, this is Mi dot, this is Me dot, because this is the rate of entropy that is entering into control volume, that means mass flow rate into specific entropy. This is mass flow rate of exiting stream plus S dot gen is equal to 0, because for steady flow there is no change in property, and entropy is a property of system. So if you differentiate any property with respect to time, that will be 0. So for steady flow process, right hand side will be 0, ds upon ds is the change in entropy, with respect to time will be 0. From this we can find out the rate of entropy generation. If it is suppose adiabatic, process, if the above process is adiabatic, then this term will be 0. Now the equation will be and if it is a steady flow, then m dot I is equal to m dot T. Mass flow rate, conservation of mass, according to conservation of mass, whatever mass flow rate enters into control volume, that is also same as the mass flow rate leaving the control volume. So mi dot is equal to me dot is equal to suppose m dot, and this is SE minus SI. This is specific entropy, SE minus SI. So this generalized equation and later on whatever equations have been derived depending upon the specific condition. जैसे कि एक रिवर्सिबल प्रोसेस होने से ऑलवेज एंट्रोपी जनरेशन विल बी 0. Adiabatic होने से whatever heat interaction terms are there in generalized equation have to be eliminated to 0. So depending upon the situation, the generalized equation, that is equation number 1, will be reduced to different forms so that your computations would be easier. Once you understand this entropy balance principle, every problem relating to entropy change and entropy generation calculations would be a easy thing. So that's all. Thanks for watching.